Alright, what's up, everybody? Week 5 here, which marks the first month of this progress. Um, just wanted to thank if there's anybody there watching. You're being of big help. I'm gonna go straight into it. So yeah, the past 2 weeks they weren't very good for linear algebra. Didn't learn much, but this week I would say, even though I didn't learn much, I learned something that I considered hard. It took me a little bit to understand this, and I hope I get to explain in a good way. So yeah, we start with change of bases. Now I think on the past videos I've talked about bases, that they're a set of vectors and that they're linearly independent, which means that if you take a linear combination of those vectors, the constants must be zero. If you put that linear combination equals zero. And not only are they linear independent, they need to generate the space, their space. So yeah, those are bases. And now this week I learned about how you can take a vector from a base and turn it and put it on another base. So, well, essentially what we have here is two bases of R2, A and B. Okay, so they're both linearly independent and they both generate R2. And then you have a V vector, which is also part of the two-dimensional space. Okay, it also belongs to the two-dimensional space. And you find out that this vector here, this random vector, okay, by the way, it's not part of A, okay, it's really just another vector, it's a random vector. You find out that V can be expressed through a linear combination of the vectors in A and through a linear combination of the vectors in B. Well, if you would agree with me that V is equal to V, so this all is equals to this all. Okay, what does this mean? This means that you can literally, even though these are two different bases, you could literally express the vectors in A through a linear combination of the vectors in B. And that's what we do here. We take the first vector in A and we do a linear combination of the vectors in B. We take the second vector in A and we do a linear combination of the vectors in B as well. Now I want you to notice something very particular about this linear combination here, which is the constants. You know how I just use some arbitrary constants here? Here they are not arbitrary. They, of course, they are real numbers, and well, they could be literally anything. But as you could kind of infer here, they are part of a matrix, which I'm going to explain a little bit why it is a matrix. What's important here is that you get the rule to get the indexes of these constants right. So the index of any element in a matrix, it is composed by two numbers, right? The rows and the columns. So this is an element. It's on row 1, column 1. Okay, how do I come up with this? This is based on. Let me actually get some white here, guys. This based on this. The first index for this element here is gonna be based on the vector it is multiplying. So since this is the first vector of B, this number is gonna be 1. Same thing here. The first index of this element here is gonna be related to this vector here, to the vector it is multiplying. So since this is the second vector in B, this is gonna be 2. And the second number for both of them, second index for both of them, is going to be related to this vector. Since this is the first vector in A, these are both going to be 1. So 1, 1, 2, 2, 1, 1, 1. I hope you understand this. This affects these two, and this vector affects this, and this vector affects this. I hope it's understandable. So yeah, here we expressed the vector first vector in A through a linear combination of the vectors in B, and now we're going to do the same but for the second vector. Again, we're going to follow the same rule to set the position of these constants here. This vector influences this number, this vector influences this number, so 1, 1, 2, 2, and this vector is going to influence both these numbers. So since this is the second vector of A, both of these are going to be 2. Okay, now that we did this, we have properly defined what are V1 and V2. What does this mean? This means that we can take all of this and implement it here. We can take all of this and put it over there, because now we know what V1 and what V2 are, and that's what we do over here. V, okay, because we're still using a linear combination to express V, is going to be x1 times V1, and V1 is all of this, so it's all of this, plus x2 times V2, which is all this, so it's all this, and this is the new equation we have. And now that we are here, we can go back to this equation here, which is V expressed through a linear combination of the vectors in B. We can do that because we have both vectors here. So what we do is that we isolate the vectors. So W1 is multiplying A11 x1 plus A12 x2, and same thing for vector 2. Well, now we can for sure infer that Y1 is going to be all this because it's multiplying W1, and we're still with V on this side, and Y2 is going to be all this. So we end up with this system here, and now it really looks like a matrix because we have the first index here, A row 1 column 1, A row 1 column 2, and same thing for these two here. And if you look close enough, this looks like a matrix multiplication, the product of two matrices to be exact. And this is gonna be y1 y2 in a separate matrix. All the constants on the first matrix. Notice that this matrix needs to come first always. Okay, why? Because this is a 2 by 2. Okay, this is a 2 by 2, and this is a 2 by 1. According to the concept of multiplying matrices, these two numbers, okay, so the last number of the first matrix and the first number of the second matrix, they need to be equal, and the result is going to be these two. So the result is going to be a 2 by 1, which it is, which is this one here. It's a 2 by 1. So yeah, and here are their names. This is gonna be vector B. This is gonna be the change of basis matrix, and this is the vector A. What this equation here is saying is that we can get a vector V from a vector V if we do have this change of basis matrix. But this also implies that we can get a vector A using a vector B if we have the inverse of the change of basis matrix. Okay, so I actually end up having an example here that I took from my teacher. So here I have two bases again. There are two sets. There are two sets of vectors, and they're both bases of R2. I haven't proved this one yet, but this one it's just a fact because it's the canonical vector. I think that's how you spell it. And E1, it is 1 0, and E2, it is 0 1. So they're the basis because you can imagine in the graph these two vectors here, these two very small vectors here, and of course they can generate any space, any vector in this space. Okay, I'm pretty sure I've talked about this in other videos. And we're given a vector A, and we're expected a vector B. So here we can usually I've been trying to reprove the formula once and once again, so I could get to the formula and get to know how to do this, how to calculate this properly. But this is not necessary. What is actually necessary is that you take the answer to this question here. What is VB if we have VA here and we have these two bases? The start to the answer is we need to express both these vectors, each one of them, as a linear combination of these vectors. So I'm just going to go jump straight into that, because it isn't exactly necessary. This helps if you forgot what to do. If you don't know what to do, you can do this, so following all the things that I explained here. If you forget what to do, you can just follow this, but this is not necessary. Okay, so let's start with expressing the first vector of A through a linear combination of the vectors in B. So it's going to be 1, 0 is a linear combination of the vectors 1 and 2 in B. And notice I'm also using the rule here. So this constant, again, the first number is 1 because this is vector 1. The first number here is 2 because this is vector 2. And the second number of both is 1 because this is vector 1 in A. And here you actually get, when you do the multiplication and you sum up these two vectors, you get that 2a11 minus a21 is going to be 1, while a11 plus 2a21 is going to be 0. Here we have a system, and then you can solve this any way you want. You're going to find out a real number for both a11 and a21. And then, okay, so now we have part of this. As you can notice here, we're trying to create that change of basis matrix. We're trying to create it, and we're getting the numbers, but we don't have all of them yet. That's because you're going to get the rest expressing the second vector in A through a linear combination of the vectors in B. So that's what we're going to do here. Okay, so second vector is going to be a linear combination of the same vectors in B, but with different constants. And we're gonna get a second system. You're gonna solve it any way you want. So you can use Gauss, you can do Gauss-Jordan, you can use whatever you want. And you're gonna find, of course, again, more real numbers for these places. And with that, with all the 4 numbers, you can build. Wait, where am I? There we go. Here, you can build the change of basis matrix, which is this one. So now we can have the vector B, which is what you're trying to look for, is the change of basis matrix, which is just got, times the vector A, which was given in the beginning of the exercise. All you have to do now is multiply this. So here we're gonna have row times column, row times column. So it's gonna be 2 times 4h over 5 plus 7 over 5. That's gonna be 15 over 5, which is 3. And here you have 4 times minus 1 over 5. That's gonna give minus 4 over 5 plus 7 times 2 over 5. That's gonna give you 14 over 5. So it's gonna be 10 over 5, which is 2. So this is vector B. This is vector B. This is vector A, but on the B base, something like that. You can even, I didn't fully understand this proof here, but you can take the vector in A and you can express it through a linear combination of the vectors in B. That's exactly what we're doing a little bit before. We took a vector from the basis A, and you express it through a linear combination of the vectors in B. I just didn't really understand why the constants they turn out to be, the coordinates of the vector B. I don't know why yet, but well, it is what it is. Yeah, so that's change of basis. The second thing I learned linear algebra this week was a little bit, just the concept of linear transformation. But actually pretty happy that I got to at least get a glimpse of it, because last year I failed. I actually gave up linear algebra after linear transformation because I simply could not understand it. But now I kind of have I kind of got a good look at this. So basically, essentially, what we have is two spaces, two vector spaces. So this could be the second dimensional space. This could be the third dimensional space, for example. And of course, we're going to have a lot of vectors here. I only took one for each as an example. And what a transformation is going to do, it's going to take a vector and transform it, like the name says, from one space to a second space. So this means that if you have a two-dimensional vector here and you do a transformation on this, you're going to get a third-dimensional vector. Okay, of course, all this depends on the rules that you're going to get, because apparently you have to we're going to have to follow different rules for each space. So for example, here it sets this rule here. If you try to transform a two-dimensional space into a third-dimensional two-dimensional vector, into a third-dimensional vector, you're gonna have to follow these rules. The first coordinate is gonna be 2 times the first coordinate. The second coordinate is gonna be minus 3 times the second coordinate of A, of the first vector in the two-dimensional space, and third coordinate is going to be the sum of the coordinates in the original vector. So for example, if we had the transformation of 3, 4 following that rule, which I literally just came up with, is going to be 2 times 3, which is 6, minus 3 times B, which is minus 12, and then A plus B, which is 7 in our case, which is 3 plus 4 is 7. So we transformed a vector in the two-dimensional space into a vector in the third-dimensional space. That's essentially what linear transformations are. And apparently, they also need to follow these rules. So if you take the transformation of two vectors and you of two vectors, you sum them, and then you try to transform them, the result should be the sum of the transformations. Okay, now something that the teacher said that we should keep in mind is that inside of these parentheses here, we still have a two-dimensional vector. From the moment on that we transform it, we're gonna get a third-dimensional vector over here. Okay, so a third-dimensional vector over here should be equal to a third-dimensional vector over here. So what does this mean? This means that even if these two, they are two-dimensional vectors, after you transform them, they should be two third-dimensional vectors. And the sum of two three-dimensional vectors, they're gonna be another three-dimensional vector. I hope this is not complicated. I hope it didn't make it complicated. And same thing for when you multiply a constant by a vector. If you multiply a constant by a vector, then you transform it, you're gonna get a three-dimensional space, a three-dimensional vector, which should be the same thing if you multiplied the transformation of the vector by the constant after the transformation. You know what I'm saying? Yeah, I still need to learn a little bit more about linear transformation. And now I'm gonna go into calculus. The first thing I learned was about the squeeze theorem, essentially what you had was three functions, and you notice that as they approach a certain a here on the x-axis, you notice this behavior over here. The limit of the first function, it is greater than or equal to the limit of the second function, which we're trying to find this one, by the way. So we're trying to solve this one. Sometimes the strategies that I talked about in the last video, they don't work, and you're gonna have to look at the graph. And this is one of the ways you can solve it if you know two functions that on this x here, okay, or close to this x, they behave like this. One is greater or equal to the function that you're trying to solve the limit, and the other one is like below that function. Okay, and then you find out, as you can see over here, that close to this, when x gets close to a, they tend to get the same limit here. Okay, but this is always true. Okay, this should always be true near a. And then you find out the limit of h of x when x approaches a is b, and the limit of g of x when x approaches a is also b. So we end up having b is greater than or equal to x, which we're trying to find still, which is greater or equal to b. Now, what is the only possibility that this inequation is true? Of course, only when x is b. Why? Because then we would have b equals b equals b. Right? That makes sense. So you find out that the limit of f of x is b. You didn't even do any calculations. You just knew the limits of two other functions, one that is above the function you're trying to solve, and one that is below, and you infer that the limit is the same as them. You know, because notice how the red and the green functions, they're kind of squeezing the blue function on this area here. That's the squeeze theorem. Here I just wanted to point out something that I got a few mistakes on. I got a few questions wrong because of this, because I thought that this behavior should always be true. Notice how like close to the x that we are trying to solve here, h of x is greater than f of x, which is greater than g of x. But as soon as we get past this line, we see that h of x is not greater or equal to f of x anymore. And I thought, okay, maybe so this graph doesn't work to calculate the limit of f of x, but it actually does, because all that matters is just this area around here. Okay, just want to point that out if anyone's having trouble with it. And well, the last thing I learned in calculus was about types of discontinuity in functions. This is basically just a lot of names. Okay, so I'm just gonna go through them briefly here. The first one is the jump discontinuity, which is basically you have a function going on here, all right, and then suddenly it breaks and it continues somewhere else. The meaning of these, you know, the filled balls and the empty circles is that whenever you have a filled circle, this means that the function is defined exactly there, because this is supposed to be the same x, okay? But f of, let's say this is a, okay? F of a is gonna be this, not this, okay? And jump, because you can also something that's important to talk about jump is that when you calculate the limit of f of x when x tends to a, you're gonna find that the limit does not exist, because you come from the left, it gives you this. You come from the right, it gives you this. So yeah, both the limits on the lateral limits are different, so the limit does not exist when x tends to a. The second one is the removable discontinuity. Now this one is kind of easy. Both sides, if you try to calculate the limit of both sides on both sides when x tends to a, you're gonna find that they're equal. So the limit of x when x tends to this a here is defined. It does exist, but it is not equal to f of a, because f of a is over here, which is what I just talked about, filled circles and empty circles. Okay, and sometimes you might not even have this at all. Okay, you might even just have an empty circle. That means that the function is not defined on that specific a. This usually happens when you, I don't know if it only happens when that is a thing, but it usually happens in exercises when you have a division by zero. Okay, so like here going right and here going right too, and they're tending to a number, but suddenly a division by zero, and you cannot and you don't have anything here. It's undefined. And last one is the infinite discontinuity. That's basically when a function is going okay here, and suddenly it decreases or increases exponentially, and you're not able to calculate the limit because the number goes up way too fast and you can't keep up. So just assume two things. Khan Academy likes to say that the limit of this would not exist, but when I took my Calculus 1 classes, it would always say that the limit was minus infinite here. Yeah, I think that's it with calculus. I think that's it with calculus and linear algebra. Now, onto Python. Onto Python here real quick. Yeah, Python here. This week I learned about multi-threading and, as you can see, abstract classes. Well, multi-threading is basically when you have oh no, wait, multi-threading is right over here. Abstract classes are a little bit there. Okay, so yeah, multi-threading, you start by importing the thread function from the threading module, and basically it's useful when you have two functions that they yield. What does that mean? That means that they take some time, and sometimes it's an undefined amount of time. Okay, you don't know. Here I know it's 4 seconds, approximately 4 seconds, but usually, especially when you're like calling APIs and stuff, you don't know how long that function is gonna take to finish. And sometimes you need two functions to perform at the same time. So how do you do that? You use threads. Okay, you create a thread. Okay, this is going to return a thread object. You create a thread, and you set the target to the function that you want to run without yielding. And just don't call the function inside here, because that's gonna ruin everything. Just put the name of the function over there, and then you start the thread. And what that's gonna do is that it's gonna run that function, but keep on with the code without interrupting the code. Because the normal thing here, if we didn't have these and we just called walk the dog over here, it would do exactly what it's told to. It would wait for 4 seconds, interrupt the code 4 seconds here, and then it would print this, and then it would move to cook. And that's not what I want. I want these two functions to run at the same time. So you're gonna have to use threads here. So both these lines here are gonna run walk the dog, and right after, without waiting these 4 seconds, the cook function is called. Okay. So let me actually take this off. If I run this, wait. Oh yeah, the thing here. So as you probably seen, no, okay, this is right. It's because okay, that's kind of weird. That's kind of weird. Okay, I don't know why VS Code does that. Anyways, since we called walk the dog, technically it should wait those 4 minutes before calling the cook function. But as you can see, as soon as I run the code, we're already cooking, and then it waits 4 seconds, and then I'm walking the dog. That's because those two functions they are working at the same time. Uh, so you cook and then you wait, and then you're waiting 4 seconds at the same time, and then you walk the dog. You know what I'm saying? Okay, but let's say I wanted to print finished here. Okay, the problem with this is that it's gonna print finished just after I have cooked, but you can see that I still have something to do. I still have to walk the dog. So what do? I have these two other lines here, which is thread adjoin. Thread adjoin is basically it's gonna do the opposite of thread. Thread avoids the function. It doesn't let the function yield. Join, it's gonna do the exact opposite. It's gonna wait until that thread is done, which means it's gonna wait until that function is done doing whatever it does, and then it's gonna continue the script. Now I might see here that I had to put another line. That's because if I run this now, okay, it didn't happen anymore. But these two lines were they were like, because this was running so fast that these two lines they were in the same these two prints, or they were on the same line. I didn't want that, but now it's not happening anymore. So yeah, so like you see, we start cooking and then we wait until we're done with the walking dog, because we're doing two tasks at the same time. We're doing two tasks simultaneously, and we wait until the second here we this task here, it takes fewer time, but we wait until the second task, which takes more time to be done, and then we print finish. So now it's correct. We cook and then we walk the dog, and then we're done. That's multi-threading. And then abstract classes. They I kind of learned it by accident. It wasn't exactly on the video on the bro code 12-hour video I'm following, and I just found that the term abstract classes on on a college object oriented programming class I'm taking this semester. And I went, of course, to learn a bit more about it. I found it interesting. To be pretty honest, I don't know if it's useful, but I found it interesting. So, well, here it is. Every time these people that people try to teach you about object-oriented programming, what they do is that they say, "Oh, we have classes, we have objects, and classes they are blueprints of the objects, and the objects follow the blueprints." I don't like that. How can I say it? I don't like that metaphor. For me, it doesn't make sense, because a blueprint is just a piece of paper, and you can't. For example, I have the blueprint of a car. You can't build a car out of a blueprint, right? You need to actually build the car, but based on the blueprint. That's what happens. So I like to think that classes, okay, normal classes, none of these two are normal classes, but normal classes, they are the actual tools, not the tools, but the machines that build the object. Uh, they build the objects, and they also build in the gadgets that would be, the class methods, the methods, the variables, everything inside that class would be the gadgets. But the start of the whole thing would be the init, the constructor function. And yeah, now abstract classes, they work way more like a blueprint than the normal classes. Why? Because they are completely useless. At first, you might think that they're completely useless because when you look at this, you just look at a bunch of defined functions that all they do is pass. That's useless. And you notice that the class it doesn't even have a constructor to begin with. What does this mean? This means that you can create, you can instantiate, you can create an object out of that class. So the first time I looked at this, I said, this is ridiculous. This is useless. Why would I want this? But then I went on and I learned a little bit more, and yeah, now it's interesting. I can't say it's useful because I haven't worked with these yet. I haven't found an actual necessity for them yet. So yeah, I don't know yet. So yeah, first you're gonna have to use the abstract base class module and import the abstract base class. Okay, this is an actual class, and the abstract method decorator. Okay, then you're gonna create your blueprint, your abstract class. This is the abstract class. So, well, I thought it was a good example to have a person. Okay, because a person is it's how can I say, it's a broad concept. Okay, you